Well, hello and welcome back to what may very well turn out to be our last lecture of the semester. Chapter 8 is a pretty short chapter, and we're well along in it right now. And from the number of pages of lecture notes I have to go over, we may very well finish it before the end of this lecture. And at this point, there's no point in starting another chapter. So that will be it for the semester. Uh, in the spirit of actually getting it over with in this lecture, let's jump in where we left off. We were going, well, as a bit of a review, we're going over theories of covalent bonding, and we were saying how to uh, account for the hybridization of atomic orbitals when atoms form bonds. And remember that it's the hybridization of atomic orbitals that allows certain shapes of molecules to exist, which really shouldn't exist if atomic orbitals were the same as they are for free atoms, like the standard s, p, d, and f shape. The hybrid orbitals have different shapes that allow us to have a variety of different shapes of molecules that otherwise would not be possible. Okay, so moving on to the molecular orbital view of multiple bonds. Through hybridization, we want to know how do you look at multiple bonds, that is double and triple bonds, through hybridization? Well, we keep in mind the fact that a single bond is a sigma bond. That is any bond that's accomplished through end-to-end overlap between orbitals like this is considered a sigma bond. And that's what single bonds are. They're sigma bonds, overlap of orbitals end to end. A double bond is actually a combination of a sigma bond and a pi bond at the same time. And that's the difference. That's what makes it a double bond, a sigma and a pi. That's the double bond. So the two bonds that contribute to a double bond are not actually the same as each other. One is sigma and one is pi. And a pi bond is formed by the side-to-side overlap of p orbitals that are next to each other. So it's sort of like you have two p orbitals that are next to each other. Their electron density can actually overlap with each other. And so for a look at a double bond, we can look at something simple like ethylene, or its official name nowadays is ethene, but it's much better known as ethylene. And that consists of two carbons with a double bond between them. And since carbon always wants four bonds, no matter what, and the double bond counts as two bonds, that means that each carbon has two other bonds, and in this case, they're single bonds to hydrogens. And you may notice from the way I've drawn it, if you have three regions of electrons around a central atom, each of those atoms will be, the central atom that is, will have an sp2 type hybridization, and it will have a trigonal planar geometry, electron geometry. In this case, since there are no lone pairs on the central atom, the carbon here, that means that the molecular geometry is the same, and so the molecular geometry around each of the carbons is also trigonal planar. And of course, the same is true for the other carbons. So this molecule is actually completely flat. Trigonal planar on this carbon, trigonal planar around that carbon, and that's all there is to the molecule. So each carbon has sp2 type hybridization, which means each carbon is trigonal planar, 3 electron regions. There's a sigma bond formed between the lobes of the sp2 orbitals of each carbon, and also sigma bonds formed between the other two sp2 lobes and the carbon and hydrogen. Okay, the pi bond is actually formed by the side-to-side overlap of the lobes of unhybridized d orbitals. So when we're talking about hybridization, we're talking about single bonds. And when we're talking about single bonds, we're talking about hybridization. It goes both ways. When you're talking about double or triple bonds, though, the hybridization only plays a role in the sigma bond that's involved in the double or triple bond, not in the pi bonds. Pi bonds are always involving unhybridized p orbitals, okay? Or sorry, d orbitals in this case. Okay, so we've got the trigonal planar arrangement around each carbon. So you can see there, here are the lobes of the sp2 trigonal planar hybrid orbitals. And one of them goes to a hydrogen, another one goes to a hydrogen, and the third one goes to the other carbon. And it's the same for the other carbon. So there's your sigma bond right there. At the same time, each carbon has unhybridized orbitals which line up next to each other. And the way the book draws them, they draw them with the lobes on these orbitals being really fat. But I've tried it that way, and I'm really not very good at drawing it that way. And a lot of books tend to draw them thinner anyway, because it's neater and it leaves more space for other stuff in the drawing. And so I'm showing them drawn as thinner lobes with just lines representing the way that the electron density can overlap from side to side. This only happens if those unhybridized orbitals are right next to each other, though. You can't have, these orbitals overlapping with orbitals on an atom that's like 3 atoms away. So it only works at short range. You have to have vacant unhybridized orbitals on neighboring atoms. Okay. Now, the sigma bond and the pi bond, are both present at the same time. It's just that I'm only drawing one at a time. Here's your sigma bond, and here's your pi bond. But actually, in order for the molecule to have a double bond, you would need both of these to occur at the same time. It's just that drawing it all in one diagram gets kind of crowded and complicated. Also note that the pi bond has 2 lobes to it. So both of these areas here, above and below the plane of the molecule, both of those together constitute 1 pi bond. So this plus this and this, all together, that's 2 bonds, 1 sigma, 1 pi, in other words, a double bond. Figure 823 on page 429 or 439 gives you a good view of that. That's drawn a little bit better than I could draw it. The way the hybridization occurs in this case is your typical sp2 hybridization. The electron configuration for carbon is 1s2, 2s2, 2p2. I've only drawn the valence shell here because anytime you're talking bonding, it only involves valence electrons. So we can ignore the 1s for these purposes. And so we have the 1s2, 2 electrons in the single s orbital in the second shell. For the p orbitals, you've got 3 degenerate p orbitals of equal energy and equal shape and equal size, but different orientations. And since there are 2 electrons spread among the 3 p orbitals, that means they fill singly first due to Hund's rule of maximum multiplicity. Each electron will occupy its own p orbital. And the idea behind hybridization is that you take a couple of different types of orbitals and sort of meld them together in a sort of average or hybrid orbital, in which each of the hybrid orbitals ends up with 1 electron in it. And so the s orbital of the valence shell and 2 of the 3 p orbitals of the valence shell will come together and hybridize into an sp2 hybrid orbitals. And as the name implies, sp2 is made up of an s orbital and 2 p orbitals, so there are 3 of them. And they all have equal energy and the same shape and the same energy, and you end up with 1 electron in each. Okay, and you also end up with the other electron left in the 2p orbital, which is unhybridized. It's still a p orbital. And that is how the pi bond forms, because each carbon has a single electron in its 2p orbital, and so you can get overlap side to side between the 2 carbons, and that is your pi bond. So here's where the sigma bonds form, and here's where the pi bond forms with another carbon that has the same arrangement of electrons. Okay, so as I said, each carbon is trigonal planar, and that means the whole molecule is flat in this case. That arrangement is needed in order to keep the p orbitals aligned to form the pi bond. As I think I mentioned before, sigma bonds, since they constitute hybrid orbitals meeting end to end, you can rotate around single bonds or sigma bonds. But in the case of pi bonds, you need this side-to-side overlap to occur, and that requires the p orbitals to be lined up in the same orientation. If you start trying to twist one of them, then the overlap is destroyed and the pi bond is destroyed. And that's not easy to do. So in practice, there's no rotation possible around a double or a triple bond, only around single bonds. Okay, so that's a double bond. Triple bond consists of a sigma bond and a pi bond and another pi bond perpendicular to the first pi bond. So in this case, we've got not only p orbitals that can be lined up next to each other in, say, in the horizontal direction in this case, but you've also got p orbitals that are lined up next to each other straight up and down. And they can overlap too if there are enough electrons. And so you can get a pi bond with the horizontal p orbitals overlapping with each other. You can also get another pi bond with the vertical p orbitals overlapping with each other. And that's how you get a triple bond. An example of a triple bond would be acetylene, or its official name is actually ethyne, ethyne, but it's universally still called acetylene. And its formula is C2H2. There's a carbon triple bonded to another carbon, but again, since carbon always wants 4 bonds, that means each carbon has one more bond, in this case, to a hydrogen. And because of its geometry, you can probably guess that if it's linear, then it must be sp, hybridized. Also, because it has 2 regions of electrons around each carbon, that would imply that each carbon must be the type of hybridization that involves 2 orbitals, because 2 regions of electrons implies 2 orbitals, and that's sp. The electron geometry for sp hybridization is linear, and there are no lone pairs on either of the carbons, so that means each carbon is linear in molecular geometry as well. And that also means then that the entire molecule is linear. And also flat, for that matter. So the carbon-hydrogen bonds are sigma bonds, and they're formed by the lobes of the sp orbitals. The carbon-carbon single bond is also formed by end-to-end overlap of sp hybrid orbitals between the 2 carbons. The carbon-carbon double bond, that is the first pi bond, is caused by the overlap of 2 unhybridized p orbitals. And the triple bond, or in other words, the second pi bond, is the overlap of unhybridized p orbitals that are perpendicular to the p orbitals of the first pi bond. So remember, we got px, py, and pz as the 3 different orientations for p orbitals. So maybe the maybe the first pi bond was created by overlap of py orbitals, and then the second pi bond, or the triple bond, would be formed by overlap of pz orbitals. Okay, and so here's my best attempt at drawing them. Again, of course, the book does it better. Figure 825 on page 430 or 440 shows it better than I can, but hopefully you'll at least get the idea here. The sp orbitals involve 2 lobes, and they are directly across from each other, 180 degrees apart, so they can get as far apart from each other as possible. That's true of both carbons. And so the end-to-end overlap of the sp orbitals from one carbon to the other, that is your sigma bond right there, and that involves the sp orbitals. But the sp orbitals also have another lobe that point in the opposite direction, and they overlap with the unhybridized s orbitals on the hydrogen. Each of them does. For the first pi bond, you'll have side-to-side overlap among the unhybridized, or between the unhybridized p orbitals on the 2 carbons, like so. And I've drawn it with the first pi bond being the vertical, or I guess you'd call that py orbitals that contribute to the first pi bond. And then we have the pi bond between the perpendicular p orbitals, which I guess you could call pz. So py and pz. And so this pi bond would be perpendicular to this. And again, all three of these bonds exist at the same time. I'm just drawing them separately because otherwise the diagram would be a complete mess. It'd be very crowded and complicated. Anyway, the electron configuration of carbon, as we said before, is 1s2, 2s2, 2p2. The core shell, the first shell doesn't really matter as far as bonding is concerned. So we look at the valence shell. That's 2s2, 2p2. The s orbital of the second shell is completely filled. 2 electrons in the p orbitals of the second shell, so each of them occupies a separate orbital. And then the hybridization occurs as the bonds form, and you get 2 sp orbitals of equal energy, each of them with 1 electron in them. And you get 2p orbitals, that is 2p orbitals, each of them with 1 electron in them. And so the sp orbitals are responsible for the single bonds, or the sigma bonds, and the 2 unhybridized 2p orbitals on each carbon are responsible for the double and triple bonds, or the 2 pi bonds. Resonance is covered in a little bit of detail in the book, and I'm going to cover it in even less, because the fact is, when it comes right down to it, resonance doesn't change the shape of the molecule or the electron regions around the central atom, and therefore it doesn't really have any effect on hybridization. Resonance, though, does only occur in cases where you have pi bonds. Okay. And only sigma bonds hybridize. So resonance involves delocalized pi electrons that can move around between neighboring atoms. But when we're talking hybridization, we're talking about sigma bonds. So it's kind of, two different things. Okay, molecular orbital theory is a way of looking at the bonding in molecules that this is actually where it comes right down to it, and we can finally recognize when certain bonds between atoms will form and certain ones will not. Okay. Also, we can use molecular orbital theory to determine the arrangement of the electrons in molecules, which in turn, again, tells you whether certain bonds will form or whether they won't. You can also use it to explain paramagnetism in molecules. That is, paramagnetism is a term that just means the molecule is affected by magnetic fields. And using Lewis structures in the VSEPR theory, what we've seen so far, it usually ends up looking like just about every molecule out there should be diamagnetic, which means not affected by magnetic fields. Molecules are generally only affected by magnetic fields when they have unpaired electrons. And one of the goals in drawing Lewis structures is to pair up all of the electrons. And so if all the electrons in all of the molecules out there really are paired up, then none of them should be affected by magnetic fields, but quite a few of them are. And molecular orbital theory shows us why. It's kind of like an extension of Lewis structures and sort of a more detailed way of looking at things that shows us that some of these molecules that might appear to have all paired electrons according to Lewis structures, in reality, they really don't, and they have unpaired electrons, and that's what makes them paramagnetic instead of diamagnetic. Okay, an example would be O2. If you draw the Lewis structure for O2, you get this, and it looks like all of the electrons in that structure are paired. Well, one of the reasons they're all paired is because one of the rules for doing Lewis structures is make sure the electrons are all paired. And so, yeah, of course, it looks like they're all paired, but in reality, they're not. And again, molecular orbital theory gives us a way to find out whether that's an accurate representation or not. Spoiler alert, in oxygen, it's not an accurate representation. Okay, Lewis structures says O2 should be diamagnetic, but actually it's paramagnetic. Okay, let's see. Molecular orbital theory can explain paramagnetism and bonding in also bonding in molecules that violate the octet rule, and why some compounds don't form, even if we can draw a plausible Lewis structure. Okay, and it has to do with the stability of the bonds that form. And molecular orbitals give us a way to judge how stable a potential bond is. And if it's not stable, then it's not going to form. Molecular orbital theory basically involves a combination of atomic orbitals into what are known as molecular orbitals. And the molecular orbitals are delocalized over the molecule. Molecular orbitals are sort of analogous to atomic orbitals, only they apply to an entire molecule. Also, molecular orbitals can explain things like why some things conduct electricity and others don't. Okay. So there's a table here that compares valence bond theory with molecular orbital theory. The valence bond theory we went over earlier in the chapter, and the molecular orbital theory is what we're working on now. In the valence bond theory, the electrons are localized in bonds between atoms, but as I mentioned a moment ago, in molecular orbital theory, the electrons are delocalized over the whole molecule. In the valence bond theory, the bonds are due to overlap of atomic orbitals and hybrid orbitals, and that would be SPDF, SP, SP2, SP3, SP3D, or SP3D2 orbitals. And actually, there are more hybrid orbitals than that, but we stopped at SP3D2 because that covers enough. In the molecular orbital theory, the bonds are due to a combination of atomic orbitals forming molecular orbitals. And those molecular orbitals we call sigma, which represents electrons that would be in a sigma bond. Sigma star, which we'll see actually represents electrons that, well, it's called sigma anti-bonding. These would represent electrons that are somewhere in the molecule other than the bond. And the same goes with pi and pi star. Pi would be, pi molecular orbitals would be electrons that are involved in pi bonds, and pi star would be pi electrons that are located in places other than the bond. Okay, valence bond theory involves formation of sigma and or pi bonds. In the molecular orbital theory, we look at bonding and or anti-bonding interactions based on which orbitals are filled. Okay, and it's the anti-bonding, how many anti-bonding electrons you have versus how many bonding electrons you have, that determines whether the bond forms or not. As a little bit of a preview. In valence bond theory, the molecular shape is based on the number of electron regions around the central atom. Molecular orbital theory, on the other hand, predicts the arrangement of electrons in the molecule. And in valence bond theory, you need multiple structures in order to describe resonance, whereas in the molecular orbital theory, one will do. All right, so molecular orbital theory describes the arrangement of electrons in molecules, as opposed to atomic orbitals, which describe the arrangement of electrons in atoms. So it's like the atomic orbital theory for atoms. It also uses wave functions, like atomic orbital theory for atoms does, and probability distributions, wave functions represented by the Greek letter psi, and the probability function or distribution represented by psi squared. And as with atoms, we're not going to go into a lot of detail with that. Just be aware of basically what they are. Electrons still have quantized energies, so not every value is allowed. Only certain values are allowed in certain molecules. And we start with homonuclear diatomic molecules That is, atom or molecules like O2 or H2 or Cl2, where the diatomic meaning two atoms involved, homonuclear meaning the two atoms are the same, are the same element. And we don't really go very far beyond that. There are, books that would go much further than that, but fortunately, this isn't one of them. So we won't have to get too far into things. The way that the orbitals are combined to form molecular orbitals is called linear combination of atomic orbitals. Basically, the atomic orbitals just sort of meet in the middle as a molecule, and we sort of look at how they come together. That's a very, very simplified explanation of how it's actually done. At the top level, theoretical levels, it is basically a combination of the wave functions of the electrons from the two atoms involved in the bond. Depending on what the wave functions of the electrons of the two atoms in the bond are like, you can have constructive interference or destructive interference, as we saw in chapter 6 when we were dealing with waves. We were dealing with electromagnetic waves then. We're dealing with basically electron waves now, which have very similar behavior. And basically, when you have constructive interference, you have a molecular orbital. Destructive interference leads to a node. And just remember, a node is just a place where there's essentially zero likelihood of finding an electron. So remember, again, as in the case of individual atoms, here we're not really mapping out exactly where the electrons are. We're relying on probability to tell us where the electrons are most likely to be and where they're not likely to be. And then other areas are sort of a gray area where there's less than, where there's a lesser chance of finding electrons at any given moment, but greater than zero. All right, so in the case of s orbitals, in phase or constructive interference between s atomic orbitals leads to what we call a sigma s molecular orbital. That's fairly easy to remember because sigma, even though it looks kind of like a weird R, sigma is the Greek letter or the Greek equivalent of S. And so sigma S molecular orbital is by the in-phase interference between two S orbitals on two neighboring atoms. The electron density is between the nuclei. Since the electron density is between the nuclei, this would be a bonding molecular orbital. And since bonding tends to lower potential energies, the bonding orbital is indeed lower in energy than the S-type atomic orbitals that contributed to it. And that makes it more stable and likely to form. On the other hand, if you have out of phase or destructive interference between S atomic orbitals on neighboring atoms, you get a sigma star S molecular orbital. In this case, the electron density is not between the nuclei. And so this is anti-bonding, and it's higher in energy than the s orbitals. And it's destabilizing to the molecule. And I've rewritten this. Okay, and I've rewritten it at the top of the page here because it got a little crowded before. So for a sigma star anti-bonding molecular orbital, it's caused by destructive interference, or in other words, out of phase interference between the wave functions of s orbital electrons on neighboring atoms. It results out of phase overlap or out of phase or destructive interference results in electron density that's not between the nuclei. In other words, there's a node between the nuclei, and that would be anti-bonding and destabilizing and higher in energy. In practice, each electron in a sigma star molecular orbital effectively cancels out an electron in a sigma S molecular orbital. So each anti-bonding electron cancels out a bonding electron. And so in cases where you have the same number of anti-bonding electrons in molecular orbitals as you have bonding electrons in molecular orbitals, those are the cases where the bond doesn't form. If you have more bonding or more electrons in bonding molecular orbitals than you have in anti-bonding molecular orbitals, then you have a bond. Okay, so you have the two atoms, and AO means atomic orbitals. The two atoms with the nuclei and the s orbitals of electrons around them, and they come together. And when they come together to form a bond, they form anti-bonding molecular orbitals and bonding molecular orbitals. So destructive interference is kind of like subtracting the orbitals from each other, and you end up with the electron density being essentially on the far side of the atoms and nothing in between them. Whereas constructive interference or addition of the two orbitals leads to sort of a blob-shaped thing where most of the electron density is actually between the nuclei of the atoms. And that is a bonding molecular orbital. So anti-bonding would be sigma star S, and bonding would be sigma S. Looking at the way, oh, okay. I see now that we've gone a little beyond the usual limit for one segment of the video. So I'm going to start the p orbital overlap in the next segment. So we'll call this the end of part A, and we'll be back in a moment with part B.